Hello, everyone. Thanks for joining us today. I am Dionysis. I'm leading the DevOps and QA teams at GWI.
And I am Fanis. I am a DevOps member on the East team.
We are here today to talk about a very interesting problem. It's a very common one, and we took a different approach to something that most probably affects many engineering teams out there. Before we dive deeper into the problem, let's have a discussion about, for us, what is a dev environment. So we're having loads of clusters, and we expect dev environments to be isolated spaces where engineers can use them and deploy multiple times per day loads of their services without being interrupted by other teams. So imagine you're having like a staging cluster and loads of engineering teams use it internally. It's very common to hear stuff like data is broken, database is not working, someone overwrote my changes and stuff like that. It's very common. Especially at GWI, we're having around 100 engineers. So having one or two only staging clusters can be a bit painful for the team. So we want to solve this. We want to solve those cases where multiple people deploy continuously on those clusters. And we want to do this in a flexible way that it's cheap and it's very fast. A few things about our stack. This is going to be a bit technical, but no surprises here. Obviously, we're using Kubernetes. We're having Thanos on top of every to be able to support loads of Kubernetes clusters. We're very dedicated to the Grafana stack. I am a Grafana champion since the beginning of the program, so we're using Grafana. We're using Loki for logs, Tempo for traces. We are experimenting with Pyroscope. But the key point here is the service mesh. So we're using Linkerd in our case. If you're not familiar with the service mesh, it's a key component about what we will talk about today. The easiest way you can think service mesh is a container next to your container image. So your pod will have two containers, one that runs your image, the other one that is the service mesh. And this container is responsible for all the traffic that gets in and out of your pod. So it has visibility about what's getting in your pod and what's getting out of your pod. Originally, we implemented this in order to get observability and monitoring capabilities out of it. Like out of the box can give you the golden observability metrics, latency, throughput, error rates, success rate, and stuff like that. And it's working nice for everyone. And yeah, we will not talk about observability right now, but we will see how we're using Linkerd to create our dev environments. So what everyone else is doing, all right, why having cheap and fast dev environment is such a common problem and it's difficult to solve it. So last year we went to GrafanaCon, and other than presenting, my main focus was, let's see what everyone else is doing, okay? So how they're handling dev environments. And I spoke, I don't know, maybe 60, 70 speakers over there, and either they were doing nothing or they were doing brute force. And brute force, it works nicely, and it's like that. If you're having a cluster and you're having a couple of monoliths or not that many services, let's say you want an engineer to have a dev environment. By brute forcing, you just deploy your whole monolith one more time, along with a couple of more services. So one dev environment can be one more monolith. Two dev environments, two monoliths. This is like brute forcing your way to create dev environments. But it didn't work for us. And because our architecture looks like that, obviously I'm extravagating a bit, but it's not that far away from reality. We're having tons of microservices, loads of microservices. So brute forcing, it wouldn't work because it means we would have to deploy hundreds of microservices just for a single dev environment. So when we took a step back, and then I put all the DevOps people inside the room, I said, you know what, we have to find a solution for this. We started brainstorming. And originally we had the idea, would it work if we treated dev environments as canary releases through service mesh? And if you've been here in the previous talk, these guys, they also spoke about canary releases, so it's a topic very close to my heart. And it's working, but let me tell you exactly, because it's a difficult thing to grasp, because normally engineering teams, they don't handle canary releases like that. So imagine you're having 3 services, all right, service A, service B, and service C. Each service is being handled, is being owned by a different engineering squad, and you are the engineer responsible for service C. So you want to deploy your awesome new feature to service C. Now, if we treat it as canary release, it would mean, okay, so if we dive deeper here, every pod has like the container that runs your image, and then Linkerd, as we've said. Linkerd is responsible for all the traffic that gets in and out. So if we treat it as a canary release for service C, it means that we deploy just one more service C through CI/CD as we're doing normally, and this is version 2. And canary releases means most of your traffic goes through service C, version 1, and the rest of the traffic goes to service C, version 2. And there are different ways to do this. In our case, Linkerd allows it with headers. So if your request has header A, send it to version 1. If it has header B, send it to version 2. And this is how canary release works. So originally, the idea was, can we create another, like one canary release for our service, and then just reuse all the services on our staging cluster, on our pre-release cluster, like hundreds of microservices over there. But when the request gets to the point of your own service, just move the traffic to version 2 instead of version 1. So reuse 99% of the resources of your pre-production cluster, but when you want to test your own feature, it will go to the version you've just released. And then we ran a POC, and it worked nicely. So it was having all these nice things that it was very cheap, because eventually we're talking about one more pod. We named this Alfred, and we just gave it to the engineers. This is how Alfred looked, by the way, when we released it in version 1.0. And Alfred includes a few things over there. It's a complicated piece of software. We kept adding features, because when you unblock this kind of stuff, normally engineers who are engaged into this are asking questions. How can you do this? How can you do that? And then Fanis will talk about how we have solved most of these issues. But originally, Alfred included a few stuff, like a Kubernetes operator, an API server, and some supported services around that allowed to do Slack bot, so you could trigger it through Slack, a database mechanism, so you can have your own database in there as well, a UI, CLI wrapper, and stuff like that. We gave all the tools we could to the engineers to use it effectively. The idea is, okay, why Kubernetes operator? Okay, we're DevOps, we like to overcomplicate things, but jokes aside, one of the original requirements when we interviewed engineers, we wanted to be able to recreate your dev environment very fast. Remember, we're having hundreds of microservices. So if we have loads of dev services out there and we want this to be affordable, we want to bring them back, we want to bring them down. Normally, devs use it like for 10 minutes, and we don't want to have them for hours and hours, because eventually it is expensive. So we aggressively scale them down after, let's say, 2 hours. But because canary releases, they involve deployments, all right, and your feature may support 5 or 10 services, so eventually 10 deployments. It can take a while, or it can be complex to deploy everything. So the original requirement was, once you create it, we want to recreate it with a single command, very easily. So this brought the discussion back to the table. I said, all right, you know what? We should save the state somewhere, and this somewhere can be a Kubernetes object. We like Kubernetes, we're working on this all day long. So we're having a Kubernetes object, which we call it DevEnv. It's a CRD, it's our own CRD. And then this DevEnv has all the information that Kubernetes knows about the dev environment, when it got created, when it will get down, who triggered it, how many services it includes, and stuff like that. And then every service, every microservice, will have its own CRD, which will be called dev service. All right. So one dev env can have multiple dev services, and those dev services will have all the information inside that can redeploy your service, like pipelines, GitHub repo, anything it may need in order, if you want to recreate it, it can recreate it out of the box. And these are complex stuff, all right? So Theofanis will dive a bit deeper here of what those DevEnv's architecture would look like.
Yes. Together we're going to take some parts of the architecture. Early on we had some fundamental questions regarding how we're going to isolate these development environments. And initially we wouldn't like to deploy separate infrastructure for this. And we thought, okay, let's try to work with Kubernetes namespaces and check our options. We could have one option to deploy this new version of the service that we have on the same namespace like the central service. And this would bring some benefits, like we could reuse some parts of the configuration, but it would be high probable to cause troubles in case we did any errors. And our development environments would easily interfere with the standard environment. Also, with this approach, we would have some problems, let's say, to manage all the resources we deploy on the same namespace, like the cleanup of the added resources we add on the namespace would be more difficult to be deleted. And also, if our service would have some dependent services to work, and these services live on different namespaces, this would make it more difficult to reason about the whole development environment status. The other option was to deploy the new version on its own namespace. This would provide better isolation. It would make the cleanup an easy task because it would be as easy as deleting a namespace, and also it would provide easier cost tracking. And we went the second way since it provided what we only wanted: safety, simplicity, and visibility. Our next question was how we're going to send the traffic to the new version of the service. We checked that Linkerd supports dynamic traffic routing through the HTTP route object, and this object can redirect traffic through headers and query parameters. And this was sufficient for our case, since we would like to support the HTTP, gRPC, and WebSocket protocols. So what the developer needed to do is to add, let's say, an extra header on his request without having to create extra domains or ingresses. And here, how this object it looks like. We have the platform API service that lives on platform namespace and exposes port 8080. And we have the new version of the service on the dev feature namespace. So the HTTP route object will bind on the specific service that is specified from the spec parent ref. And this object defines two rules. The first one is the devenv specific that says if on your request you have the devenv header with value dev feature or a query parameter with name devenv and value dev feature, which is the devenv name, so you can see it's the namespace name, then you should send the traffic on the same service, same port, but on a different namespace. The second rule is the standard one that sends the traffic to the original service. But this routing policy, to make it work, you have to make your services be able to propagate this header to all its downstream services. And this was somehow a problem from us. What we did is we updated our company libraries to be able to propagate these headers. And it was good for us that most of our services are using these libraries. And this made the adoption of this effort a very simple task. So what the developers needed to do, they had only to bump the library version they were using and redeploy their applications. Or in the worst case, they had to add a separate middleware to start propagate these headers. This gave us a consistent way to route traffic into the development environments, and it was the only change needed from code side. This extra requirement for the header didn't make any success. So the devs were not really accessible from all people and our automated tests. So what we changed was the following. we added a new functionality on our frontend, and now it detects the path we request, and if it starts with the prefix dev does something, it automatically adds this value as the dev header, or for the WebSocket cases, as a query parameter. So people don't need to have extensions or an extra setup to be able to hit their development environments. They just need to set the proper path, and the system will take care of the routing. So after this change, the development environments are accessible from engineering and non-engineering teams and our automated tests. Our next problem was how we're going to create these development environments. Here we have set a golden rule. We said let everything be created through our GitHub workflows. This will provide a very clean, repeatable, and developer-friendly way of creating these new services. And to implement this, we had to support only 2 cases. We have one case with repositories that deploy only one service, and to cover this case, we added another workflow, a separate workflow that is triggered when the branch we work starts with dev does something. So if you commit something there, instead of having a normal deployment, you are going to deploy this service on the new namespace as a development environment, and the name of the namespace will be the same as the branch name. And if you do the same on another repo, this means that both services will be deployed on the same namespace and will be included on the same development environment. And we had another case on which one repo can deploy multiple services. So for this, we made the above workflow to be triggered manually with some options like the branch name to use, what service you need to deploy from this repo, and which is the development environment that you should include this service. Some people had many dependencies, so they started complaining and say, okay, I now have to create not only one branch, but several branches on different repos. And to solve this, we introduced dependencies, a YAML file with the name DevConf.CZ that has a depends on field, and then you can specify the repos and the services you need from each repo to deploy. So from a single file, you can define a fully functional development environment with multiple services. And this was something that we needed also to test new features from our automated tests. Our next challenge was related to the databases. We are using managed instances, and we would like to provide isolated databases on each development environment. What are the benefits of this? So the developers can test breaking changes without worrying about tampering the standard environment's health. They can, let's say, leave their test data behind without worrying about cleaning up their data. And these databases can be easily recreated as part of the development environment workflows we introduced on GitHub. So our idea here was to have these instances not as managed services, but as pods inside the new namespaces. And why pods? Pods can be created or recreated very fast. They are isolated on their namespace, and they are cheaper than managed instances. And how we implemented this? We have a cron job that for each instance, every night, creates a reference persistent volume that includes the instance user's data and schema. And when we want to have this instance as a pod inside a new namespace, we create a persistent volume claim with a special spec that effectively will clone this reference volume to the new namespace. This persistent volume claim is consumed later with from a stateful set, and here we go, we have our instance as a pod. We were able to deploy by then everything by hand with success or without success, because this part was very error prone. And we thought, okay, we should add automation. We should be able to describe what we want in a Kubernetes native pattern. We would like to be able to describe it as an object with statuses and to be able to monitor it. So we thought that the perfect solution for all this and it would act like the glue that could stick everything together, would be a Kubernetes operator. And to facilitate our job, we introduced two CRDs, the dev and CRD that describes a development environment entity, and a dev service that describes a workload within a development environment. And here is how this dev and CRD looks like. On its spec, it has only the time to live, which indicates when the development environment should expire or get deleted. And we have the dev service CRD, it's more complex. It has a type. It can be either a service for a standard workload or a database if it's a type of database. Databases are again handled as dev services inside the development environment. We have some information about the branch and the repo we use to create this dev service, the namespace and the helm release name we use to deploy the standard application. We have on the service list the service and port tuples that are required to create the HTTP route objects to make routing work. We have some annotations to mark some special events like when the event was last recreated. We have some labels for quick filtering and the status when we mark the status of the development environment and the reason why we have the change on the status that can be either a GitHub event or a manual action. And let's take a look together how development with these dev environments looks like. Okay, we have the audiences here API that has an HTTP and gRPC part is deployed on the audiences namespace. And we have a new feature. Let's say we work on the new feature, and from this feature we create the dev demo branch to be able to deploy it as a development environment. So we create the branch and push it. And as we told before, since we start with the dev-something prefix, it will call our special workflow to deploy this application as a development environment. This special workflow will still run the build and test steps that our engineers have designed, but instead of doing the normal deployment, it will do a deployment as a development environment. This application has a dependency with a database called audiences. So as part of the deployment, if we see, we will call a special workflow that will clone the reference volume of the audiences instance, create a stateful set, and this stateful set will be our database. So after a while, we are going to see that the new pod with this instance has been created, and after it becomes running, we are executing the helm upgrade install command to install the service on the new namespace. After the installation finishes, the operator will create the HTTP route objects, and if we check here, we are going to see that we have 4 HTTP route objects on the original namespace. And after this part, the development environment is considered active. We can manage it with the /Alfred command and some other options. We can list the dev environments we have. We can describe them with get, extend the lifetime with extend, or delete them. With list, we can list the development environments and find our own one that will expire in 8 hours by now. We can describe it with get to check the exact TTL and also check what dev services are included. Here we have our workload and the database. If we click on these links, they are going to send us on the GitHub workload that ran and deployed these services. So if something fails, someone can click on it and check what failed. Let's say we have done some work and it's the end of the day and we would like to continue and have our workloads running there and to sum up the charges. So we can bring it down with the retire command. And here we can see that after the retire command, all the pods were gone. The next morning, we want to resume our work, and we can recreate the development environment. So we can execute the recreate command, it will iterate over all the dev services we have on the development environment and create and call the necessary GitHub workflows to run again these steps, the build, test, and deploy. It's the same workflow as before. So if we check the statuses of the dev services here, we can see that for the audience that we call the workflow, the status has changed to creating, but since the database workflow hasn't been called yet, it's still on retired status. After a while, if you remember, we saw that at some point the workflow that will clone the database will be triggered, and voila, we have both of them on creating status, and when everything is done, both will be marked as created. So this is how developers can check the status of the development environment. The same can be seen from the Slack, and when everything is done and we don't want it anymore, we can manually delete it with the delete command. And on this case, we are deleting all the workloads inside the dev demo namespace, including the custom resources, dev and dev services, the namespace itself, and also the HTTP route objects that we have created. So if we check here, we have no pods on the dev demo namespace. We have no HTTP route policies. And if we check, and for the namespace itself, okay, it's deleted, it's not there. And this is how development with development environment looks like in our company.
All right, a bit too much information. Let's take a deep breath. What we have described, other than the complexity of how you're handling all this complex stuff, what we managed to achieve is like dev environments treat as canary releases that they're cheap. And why they're cheap? Because by the end of the day, you just reuse your pre-production cluster and your dev environments one more pod. And pods are cheap, especially if you aggressively scale them up and scale them down. So in our case, it worked beautifully. We tested it with a single squad, it had amazing results, and then we decided to scale it to the rest of the engineers and fix things as they keep requesting more features. So let's get a few takeaways. This is a passionate talk of mine. It's what I wanted to hear like last year when I was like in Grafana-Con, when I was asking, what are you doing with dev environments? People haven't thought, like no one from those people haven't thought about it. And everything they suggested was very expensive for us. Again, we're having hundreds of microservices over there. So this is something that I would like my previous self to hear. Have you tried this? Maybe this is working for you as well. For us, it's very cheap. It's working very well. It's scaling across 100 engineers, more than 100 microservices, and we keep adding stuff. So yeah, dev environments, they don't have to be expensive. If you get anything out of this talk today, it's this. Dev environments, they can be as cheap as a couple of more pods inside your clusters. So next step for us, we have already lots of people using Alfred internally. Someone built a UI in our hackathon last month. We have a very interesting problem to solve, like recreating stuff still deploys everything from the start, and deployment can take a lot of time. So one of the things we want to implement later this summer is using Keda for event-driven autoscaling. So instead of you having 10 services and you want to build only one, don't recreate the rest. Deployment to 0 and then deployment to 1 based on events from Alfred. This will make, I don't know, recreation maybe like 90% faster. And we're thinking about open sourcing everything. It's not a ton of things over there, but it's very opinionated on our stack. It's very close to Linkerd, it's very close to Kubernetes. Obviously, we're using GitHub Actions, it's very close to that as well. So it's working very well for us, but it's opinionated on the tool set that it requires in order to use it out of the box. But, challenge accepted. Okay, so we'll think about it. And that's it. Thank you a lot. I know it's late in the day. It's been late in the 33-day schedule, and it was very technical. Happy to answer any questions or kick off a discussion about if you are using a dev environment or how you handle this kind of issues. And thanks for listening to us. Yeah. Yeah. All right. Okay. Yeah. All right. Okay. Yeah. All right. So the nice gentleman here is asking, we're having loads of microservices, so hopefully we're having loads of databases as well. Having all these databases with requirements to other databases, it sounds like a very heavy part. How is it working? Is it fast? Is it slow? Right?
How do you see that when you spin up them for each feature?
All right. Okay. Yeah. And then how we can keep track of them. So we gave all the everything. It's up to the engineers. So you're right. We're having dozens of services and those databases, they're managed ones. So Alfred is working fine when it comes to pods, but when it comes to databases, you cannot have one more database managed per dev environment. What Fanny's described is working very nicely. So every night we're taking a snapshot, all right, and then this snapshot, when you recreate it, is just a clone of the PV, so it's ultra fast. So every night we're having a big cron job, we take dumps of all our databases and we have them as PVs. So when you're requesting a dev environment, build may take 3 minutes to build it, to build your image and deploy, but to create a snapshot of this PV and attach it to a Postgres pod, it's lightning fast. I don't know, maybe it takes 20 seconds. I don't remember the exact details. I would suspect it's a cron job that does gcloud where in GCP. Gcloud.
It runs a PG dump effectively.
Yeah.
Okay. Yeah.
But it is very fast.
Yeah.
And then because those databases, they are dev services, it's just a different type. It's not a microservice. It's a Postgres. It's a database type. It's part of Alfred. So you can do kubectl, get dev services, and then you'll see the databases are there, and then they're running, or they're not running, or they're retired, stuff like that.
Just to add, sometimes, because these are not the data that our product is managing, is the microservices data. We have some cases from 30 to 50 gigabytes. To prepare the persistent volume reference we referred earlier, it takes up to 30 minutes, and to clone it takes it 1.5 minutes. The most time-consuming part in this is just to kick off the workflow, let the workflow be scheduled somewhere, and then have the stateful set start. So this process takes maybe 2.5 minutes, but the cloning part is 1 to 1.5 minutes.
So 2.5 minutes is not that bad. Most of the times, built by engineers takes 5 minutes. Okay, so yes.
It was difficult for me to follow the presentation, so I will try to reformulate what I understood and tell me if I got that right.
Yeah.
So you have your default status that you have an application with hundreds of microservices shared around many space. You don't want to reprovision all these microservices just to test a new feature, right?
Yeah.
So when somebody
Exactly. So I don't have to repeat the question. You repeated the presentation very nicely. So other than the technical stuff, let's leave the technical stuff aside. What you have described, or what canary release are doing, you can do it with many different ways. We do it through service mesh. The previous guys, they were doing it through the load balancer. Yeah. Yes. You're right. Okay. But yeah, what green-blue deployments or canary releases, they are working with server, with headers or with GET requests. Yeah, we're out of time. So you are right. You got it right. But other than the technical details aside, we're having one more pod, and then we treat it as a green-blue deployment. Okay. But if you want to test your own pod, you just have a specific header. And then every service will go down the line, have this header, and then you'll see your own new code. Thank you. We'll be around if you want to have a chat. And thank you again.